In the outermost reaches of our solar system, roughly 5.5 billion kilometers from the Sun, there is a small, frozen world that by all reasonable expectations should be dead. It should be cold, still, and geologically inert, a relic of the early solar system, unchanged for billions of years, coated in ancient craters and dusted with the residue of time. That world is Pluto. And for decades, that is exactly what scientists assumed it would be when they finally got close enough to look. They were wrong. When the New Horizons spacecraft streaked past Pluto on July 14, 2015, after a journey of 9.5 years and 3 billion miles, the images it returned stunned the scientific community into near silence. There were towering mountain ranges made of water ice, some rising as high as 11,000 feet. There were vast, smooth plains of nitrogen ice with almost no craters at all, suggesting they had been resurfaced within the last few million years, yesterday, in geological terms. There were what appeared to be enormous dunes. There were features that looked disturbingly like lava flows, except instead of molten rock, something else had oozed and crept across the surface. And beneath all of it, something was, and still is, happening. The story of what lies under Pluto's frozen skin is one of the most genuinely mysterious open questions in planetary science. It is a story about heat that should not exist, about liquid water in a place cold enough to freeze nitrogen, about geological forces operating 4 billion miles from the nearest significant heat source, and about scientists who keep finding evidence that does not fit the model they expected. Nobody knows exactly what is going on. Nobody can say with certainty what is driving it. And the deeper researchers look, the stranger the answers become. To understand the mystery, you have to understand just how cold Pluto actually is. Surface temperatures hover around -230 degrees Celsius, close to absolute zero, the point at which molecular motion itself nearly stops. At those temperatures, nitrogen freezes solid, methane freezes solid, even carbon monoxide freezes. Water ice on Pluto behaves more like rock than ice in any familiar sense. It is rigid, structural, and ancient. For a world this cold, this far from the sun, traditional geology, the kind powered by solar energy and internal heat radiating outward from a molten core, should have ceased billions of years ago. And yet, the most obvious piece of evidence that something unusual is happening lies in a region now called Sputnik Planitia, the left lobe of the enormous heart-shaped feature that New Horizons made famous in its first images of Pluto. Sputnik Planitia is a roughly elliptical basin about 1,000 kilometers across, filled with nitrogen ice, and it is strikingly, almost suspiciously smooth. The reason that smoothness is so significant is that the rest of Pluto's surface is covered in craters. As you'd expect, for a world that has been sitting in the outer solar system for 4 billion years, getting pelted periodically by comets and asteroids. Craters accumulate over time. They are a geological clock. A heavily cratered surface is an old surface. A surface with no craters is a young one. Sputnik Planitia has almost no craters. Scientists who studied the imagery calculated that the nitrogen ice in Sputnik Planitia must have been geologically resurfaced within the last 10 million years. Some estimates push that number even lower, to within the last few 100,000 years. On a cosmic timescale, this is essentially Cho. Whatever is happening beneath Pluto is not ancient history. It is ongoing. But that immediately raises the question that nobody has been able to fully answer. What is driving it? On Earth, geological activity is powered primarily by two things. The first is residual heat from the planet's formation. The heat generated when billions of chunks of rock and metal slam together over millions of years to build a world, and the heat released by the decay of radioactive elements trapped inside. The second is the immense size of Earth itself, which means that heat escapes slowly over billions of years. Mars, which is smaller, cooled faster and geologically died earlier. The Moon, smaller still, is essentially geologically dead. Pluto is not only tiny, smaller than Earth's moon, but it formed in the cold outer solar system, which means it accreted more ice than rock, and that changes the thermal math entirely. There is also no significant tidal heating on Pluto, unlike on Jupiter's moon Europa or Saturn's moon Enceladus, where gravitational squeezing by a massive nearby planet generates the heat needed to maintain a subsurface liquid ocean. Pluto has no gas giant parent planet pulling at its interior. It has its large moon Charon, and the two do interact gravitationally. But the pair reached a tidally locked equilibrium long ago, meaning the tidal forces are minimal and stable. Not nearly enough to explain what the surface is telling us. So where is the heat coming from? One of the leading theories that emerged in the years following the New Horizons flyby centers on the possibility of a subsurface liquid water ocean. Not a small pocket of slush, a genuine global ocean, potentially hundreds of kilometers deep, sitting beneath the ice and insulating itself from the vacuum of space with a thick frozen shell. The idea initially seemed radical. Water staying liquid at the temperatures and pressures found inside Pluto requires a heat source, and finding that heat source has occupied researchers ever since. Studies published in the years after 2015 began to build a circumstantial case. The shape of Sputnik Planitia itself is one piece of evidence. The basin is believed to have been formed by a large impact, a collision with a sizable object that gouged out a crater. Over time, that crater became a reservoir for nitrogen ice. But here is where things get interesting. The excess mass of all that ice should have created a gravitational anomaly, a region of slightly higher gravity. On a world with a fluid interior, or a layer of liquid beneath the crust, that anomaly would cause the crust to reorient itself, drifting until the heavy region sat near the equator, where the rotational dynamics of the planet make it a stable position. And that is exactly where Sputnik Planitia sits, almost precisely on Pluto's equator. This reorientation, called true polar wander, is much more easily explained by the presence of a fluid layer beneath the crust than by any other mechanism. A completely frozen interior would not respond the same way. The geometry of Sputnik Planitia is quietly, compellingly pointing at something liquid underneath. Then there is the question of Pluto's crust thickness. In 2019, a research team published findings suggesting that if Pluto had a subsurface ocean that was now fully frozen, the freezing process would have caused the volume of water to expand, cracking the surface and creating a specific pattern of extensional faults. Faults that look like the surface was being pushed apart. When they looked at Pluto's surface geology, they found exactly those kinds of features. The cracks in the right places, oriented in the right directions. This matched a model in which the subsurface ocean has been gradually freezing over geological time, but has not yet frozen completely. That word "yet" carries enormous weight. In 2020, another study brought an entirely different kind of evidence into the conversation. Scientists analyzing data from the New Horizons mission found traces of ammonia on Pluto's surface, specifically at a site associated with what appeared to be a relatively recent cryovolcanic flow. Ammonia is important for one critical reason. It is a powerful anti-freeze. Dissolved in water, ammonia dramatically lowers the freezing point of the mixture, potentially allowing water to remain liquid at temperatures far below 0 Celsius. If ammonia-rich water is being vented from Pluto's interior to its surface through cryovolcanic activity, that strongly implies that there is ammonia-rich liquid water in Pluto's interior right now. The ammonia detected on the surface was not ancient. Ammonia exposed to space is broken down by ultraviolet radiation and charged particles relatively quickly. The presence of fresh ammonia means it was put there recently. Cryovolcanism on Pluto. That phrase would have seemed outlandish before 2015, but New Horizons gave researchers reason to take it seriously. Two large mound-shaped features in the southern hemisphere of Pluto, Wright Mons and Picard Mons, have been tentatively identified as cryovolcanos. Picard Mons is enormous by any standard, roughly 160 kilometers across and possibly 6 kilometers high. If confirmed as volcanic structures, they would represent the largest known cryovolcanoes in the outer solar system. Both features have strange textures, rough, hummocky terrain with a central depression that resemble the caldera structures found at the summit of traditional volcanoes, but formed by the eruption of ice-forming material rather than magma. The word eruption in this context does not mean a dramatic explosion. Cryovolcanism is a slow, gentle process. Icy slurry oozing upward through cracks, spreading across the surface, freezing as it spreads. But even a slow process, repeated over millions of years, can reshape a world. The smooth terrain around Wright Mons and Picard Mons covers an area comparable to the state of Missouri, and it appears to be geologically young. Yet here is where the mystery deepens rather than resolves. Because even if researchers accept that Pluto has a subsurface ocean, the question of what is keeping it from freezing remains stubbornly open. Radiogenic heating, the slow decay of radioactive elements like uranium, thorium, and potassium inside Pluto's rocky core, provides some heat. All rocky objects contain these elements, and they have been slowly generating heat since the solar system formed. But calculations suggest that radiogenic heating alone may not be sufficient to keep a substantial amount of water liquid inside a world as small as Pluto, especially at its distance from any significant tidal influence. Some researchers have proposed that the answer lies in insulation. If Pluto's icy shell contains a layer of gas hydrates, clathrates, those structures are extraordinarily poor conductors of heat. A thin clathrate layer could act as a thermal blanket, trapping just enough internal heat to keep the ocean from freezing. This is an elegant solution, and it has been modeled mathematically in ways that produce results consistent with what we observe. But it has not been confirmed. We do not have a probe sitting inside Pluto's interior taking measurements. Others have suggested that the initial formation of Pluto may have been more violent than previously thought, that if the accretion of Pluto's material happened relatively rapidly, the heat generated could have been substantial enough to melt a significant portion of the water ice, creating an early ocean that has been slowly freezing ever since. Under this model, Pluto is not generating new heat in any dramatic sense. It is losing heat slowly enough that some portion of that primordial ocean persists today. The slow freeze is what creates the surface features. The gradual release of the expanding ice is what cracks the crust. What makes this particularly striking, and what keeps the conversation alive in the planetary science community, is that Pluto is not supposed to be this interesting. For most of the 20th century, Pluto was regarded as a small, cold, dead ball of ice at the edge of the solar system. Scientifically significant mostly as a boundary marker, not as a world worthy of the same attention as the moons of Jupiter or Saturn. The push to fly a spacecraft to Pluto at all was controversial within NASA for years. Resources are limited, and sending a probe to a world that most scientists expected to be geologically dormant required making a case that the journey would yield meaningful science. New Horizons made that case retroactively, and then some. The data it returned has kept planetary scientists busy for over a decade, and the images it captured, Pluto rendered in stunning detail for the first time, its heart-shaped plane glowing in false color, its mountain ranges casting long shadows across the plain, changed the public's relationship with this small, distant world in ways that are difficult to quantify, but impossible to dismiss. The deeper implication of Pluto's subsurface activity reaches well beyond Pluto itself, because if a world as small, as cold, and as distant from the sun as Pluto can maintain a liquid water ocean, then the number of places in the solar system where liquid water might exist, and where life, therefore, might be possible, expands dramatically. The traditional habitable zone around a star is defined by temperature, the distance at which liquid water can exist on a planetary surface. But Pluto sits more than 40 times farther from the Sun than Earth does. If Pluto has liquid water, the habitable zone concept may be far too conservative. It may need to be replaced by a model that accounts for internal heat, tidal forces, radioactive decay, and insulating chemistry. A model in which oceans are not the exception in the cold outer solar system, but potentially the rule. Europa, Enceladus, Ganymede, Callisto, Titan, all of these worlds have subsurface oceans in various states of conformation. Pluto may be joining that list, and beyond our solar system, in the vast population of dwarf planets and Kuiper Belt objects that we know exist but have barely examined, the same processes may be at work. Small, cold, seemingly dead worlds harboring liquid water kilometers beneath their frozen skins. That changes everything about how we think about the distribution of life in the universe. There are still enormous gaps in our understanding. New Horizons flew past Pluto. It did not enter orbit. The spacecraft collected data during a frantic encounter that lasted a matter of hours, capturing images and measurements with instruments that were designed years before the flyby, before anyone knew what Pluto would actually look like. Much of the data was returned over the 18 months following the flyby, trickling back across billions of miles at the speed of light. Scientists have been working with that fixed, finite data set ever since. There is no follow-up mission currently funded or scheduled, no orbiter, no lander, no probe that will descend into Sputnik Planitia and drill through the ice to measure what lies beneath. What we have are photographs, measurements of atmospheric chemistry, topographic data, and the mathematical models that researchers have built on top of all of it. What we do not have is certainty. The subsurface ocean hypothesis is the most coherent explanation for the evidence. The smoothness of Sputnik Planitia, the true polar wander, the cryovolcanic features, the fresh ammonia deposits, the extensional fault patterns, but it has not been proven. It is the best guess of some of the most careful and rigorous planetary scientists working today, and those scientists are the first to admit that there is a significant difference between the best available explanation and the truth. Something is happening beneath Pluto's surface. The evidence for that much is compelling enough that very few researchers seriously dispute it. The processes shaping the ice fields of Sputnik Planitia are not ancient. They are not relics. They are active, ongoing, and powered by something that we have not yet fully characterized. A world that should be dead is not dead. A world that should be frozen solid may contain a liquid ocean larger than any on Earth. A world that exists in conditions we once thought were incompatible with geological life is doing geology anyway, quietly and persistently, billions of miles from anyone who might notice. And nobody, not yet, can tell you exactly why.